All right, so now we are starting our second last unit of our chemistry course. This is unit number 4 that we are beginning. The subject of this unit and all of the lessons here in this unit is electrochemistry. Electrochemistry is the interconnection between electricity and chemical reactions, and it deals with the transfer of electrons from one substance to another. And this can take place in a spontaneous fashion or in a non-spontaneous fashion. Specifically in today's lesson, we are going to learn about a very important type of reaction that takes place that involves the transfer of electrons, and these are oxidation and reduction type reactions. In oxidation reduction type reactions, as I said, electron transfer occurs between two components. One is oxidized, one is reduced. And since these reactions often happen in conjunction with one another, they are just in short form termed redox reactions. Okay, redox reactions. And in today's lesson, we're going to talk about how to identify these oxidation and reduction reactions, as well as learning how to communicate using appropriate scientific vocabulary. These ideas that have to do with electrochemistry. We are going to understand oxidation and reduction in terms of electron loss and electron gain, or a change in oxidation numbers. And we're going to learn how to write balanced equations for oxidation reduction systems, including the half-cell reaction. So, as I keep stressing, oxidation and reduction reactions involve the transfer of electrons. So electrons are being transferred. And in order to talk about this, the really best way is to jump in on an example. So for example, if we have a reaction that involves...
Can you hear me?
I can hear you now, Borna. Yeah.
Okay.
Am I being heard clearly?
Yeah, I just want to, because my mic wasn't working the whole time.
Right. Yeah, I did notice that I didn't see a mic for you. Okay. So yeah, here in this reaction, in this example reaction, we have zinc in its solid state. So solid zinc metal is being reacted with copper sulfate, and this is an aqueous. When you see this aqueous symbol here, it indicates that this compound is dissolved in water so that it's ionized into its separate ions of copper and sulfate. So zinc plus copper sulfate in the aqueous form is going to copper in the solid state and zinc sulfate in the aqueous form. So let's take a look and really notice what is happening to the reactants in this equation. The first step is to write out the total ionic equation. And by total ionic equation means that when we see a component that is in the aqueous state, such as this copper sulfate, such as this zinc sulfate in the aqueous state, we go ahead and we write it out in its ionic form. So copper plus 2 ions and sulfate ions. And we denote again that they are in the aqueous state. Same with the zinc sulfate. We write it as zinc plus 2 ions and the sulfate ions, both in the aqueous state. And here, notice that the zinc atoms here have lost, excuse me, 2 electrons to form these zinc ions. So here, zinc from the solid state having no charge, overall charge of 0, by losing 2 electrons has now become zinc plus 2 ion. And that this copper plus 2 ion has in return gained 2 electrons and become reduced to this solid copper metallic copper here. So the copper ion has gained electrons to form this copper atom, and the zinc atom has lost electrons to become the zinc ion. And we can just focus on the half reactions equations for this oxidation of the zinc atom to the zinc ion by pulling it out and looking at it like this. So the zinc atom loses electrons to become zinc ion plus the 2 electrons that it's lost. So overall, this side of the equation is now equal to this side of the equation. And the same with the copper. The half reaction for this copper is the copper ion has gained 2 electrons to become copper atom. All right. And then if we notice that in this total ionic equation, the sulfate ions can cancel each other out from both sides of the equation, and you end up with the net ionic equation here. And the net ionic equation is that zinc atom plus the copper ion goes to copper atom plus the zinc ion. And the important thing to remember here is that one is becoming oxidized and one is becoming reduced. Okay, so zinc is becoming oxidized, losing electrons is becoming oxidized, and copper is becoming reduced by gaining electrons. An oxidation reaction always describes a loss of electrons, and a reduction reaction is a gain of electrons. And these reactions always occur in tandem with each other together, and they're referred to as redox reactions. Let's look at another example, and here we're going to see how would we be able to identify an oxidation reduction reaction. So in this example, the question is to identify the reactant that is oxidized and the reactant that is reduced in this reaction here. So here we have lead ions plus copper nitrate goes to, lead atom plus copper nitrate goes to copper atom and lead nitrate. The first step in our solution is to write out the total ionic equation just as we did in our previous example. So we write out that lead atom plus copper ion, copper plus 2, plus 2 nitrate ions. So here you can see there's the nitrate ion, and the bracket around it indicates that it is, there's 2 of them. So 2 nitrate ions goes to the copper atom, which is what we had here before, plus the lead ion, and again, 2 nitrate ions. Then from here, we write the net ionic equation. So we notice that the 2 nitrates cancel each other. The 2 nitrate ions on either side of the reaction cancel each other out. And we are left with what is here, the net ionic equation. So lead atom plus copper ion goes to copper atom and lead ion. And then we identify what is the charge on each element, that the lead atom is going to towards lead ion, which has a +2 charge. So this is oxidized. Oxidation is a loss of electrons. So here you can see by losing 2 electrons, it has gained a +2 charge. And copper ion, which started with a +2 charge, is now going to gain those 2 electrons, become reduced, and form a copper atom. And one easy way to remember these redox reactions, what is becoming oxidized and what is becoming reduced, is to remember this little acronym here. Leo the lion says GR. And you can remember that Leo, L-E-O, stands for Loss of electrons is oxidation, or lose electrons, oxidation. And the GER part is GER. Gain electrons is reduction. So lose electron, oxidation, gain electrons, reduction. Leo says GER. So losing electrons again causes an increase in the oxidation number from 0 to +2. So here in our example, the lead atom has an oxidation state of 0, and it causes this loss of electrons causes an increase in this oxidation number to an oxidation of +2. And the opposite is true for the copper. So in copper, gaining of electrons causes a decrease in this oxidation number. So currently this copper ion starts out with an oxidation number of +2, and through gaining electrons, its oxidation number is decreased to 0. So in this reaction, what we have is the total number of electrons gained is equal to the total number of electrons lost. So 2 was gained and 2 was lost, and they're equal. As many electrons is gained as is lost. There are 3 examples here for you guys to play around with and try your hand at identifying the oxidized and reduced reactants and going through the same motions as we did in this example with these 3 to make sure you really understand. So up to this point, these couple of examples that we looked at had to do with redox reactions involving metals. The metals were copper and zinc and lead, and those are all metals. But redox reactions can also involve nonmetals. If you recall, in Unit 1, we learned that in ionic bonding, there's a transfer of electrons between metal and nonmetal. But in a covalent bond, electrons are shared. They're not fully transferred. Now let's consider this covalent compound, carbon dioxide. Here we have the Lewis diagram of the carbon dioxide molecule. And you see that the electrons are shared in a covalent bond here, right? And it's very useful to assign the apparent charge on each of these atoms. And this apparent charge is called the oxidation number. So when we examine what's the electronegativity difference between carbon and oxygen in this carbon dioxide molecule, we notice that oxygen is a more electronegative atom than carbon. And since oxygen gains 2 electrons to become O2 minus 2 in this ionic compound, the oxygen is assigned an oxidation number of -2. So oxygen has an oxidation number of -2. And since all of these oxidation numbers in this molecule of CO2, which has no overall charge, it's neutral. So all of these oxidation numbers have to add up to ultimately become 0. So if we understand this, and if we know this, and knowing that the oxidation number for the oxygen is -2 for this one and another -2 for this one, then we can see that the oxidation number for the carbon atom in the compound has to be +4 in order for them to add up to be 0, for there to be no overall, since this is a molecule that has no overall charge. The oxidation number of carbon then is +4, and you can see that here we're saying, okay, carbon plus 2, because we have 2 oxygens, 2 minus 2 oxidation numbers for the oxygen. So, and if we add these all up, we have to end up with 0. So the oxidation number then for our carbon is +4. And this assigning of oxidation numbers is not exactly exact. It's not an exact science, but there is a table that we're going to go through that will give us some general rules and some general guidelines to help us with figuring out how do we assign these oxidation numbers. So let's look at that together. So in this table, the rules for assigning oxidation numbers. The first rule, number 1, is that the oxidation number of an atom in an uncombined state is always 0. So whenever you have an atom on its own, such as potassium, such as O2 gas, such as N2 gas, oxygen gas, nitrogen gas, or if you have lithium, all of these atoms are uncombined. They are on their own. And in this uncombined state, they all have an oxidation number of 0. So that's the first rule to keep in mind. The second rule is that the oxidation number of a simple ion is simply its charge. What do we mean by that? For example, the oxidation number of magnesium in a magnesium ion, which has a charge of +2 in a magnesium +2, the oxidation number of this is simply +2. So the oxidation number of a simple ion, such as this magnesium ion, is the charge. So it is +2. In a sodium ion, it is +1, for example. And the third rule is that for hydrogen, the oxidation number of hydrogen in most compounds is +1, except in metal hydrides. So the oxidation number of hydrogen in H2O, in HCl, in HNO3, the oxidation number for the hydrogen would always be +1, but in the metal hydrides, such as sodium hydride, potassium hydride, lithium hydride, and the exceptions here are the metal hydrides. In this case, the oxidation number for hydrogen is -1. Okay. And once you get to do some practices, you will remember these rules. It's like solving a puzzle, solving a numeric puzzle. And if you remember these rules, then you can go ahead and apply the rules, and you'll know how to do it. Rule number 4 is that the oxidation number of oxygen in most compounds is -2. So the oxidation number of oxygen in H2O, in magnesium oxide, in NO3, HNO3, all of these, the oxidation number for oxygen is -2, with the exception that in hydrogen peroxide, it is -1. So if you see oxygen, you can assign it an oxidation number of -2, unless it's in hydrogen peroxide. In that case, it is -1. And number 5, the oxidation number of group 1 element ions is +1. So for example, the oxidation number of potassium is when it's in its ionic state is +1. When it's in its uncombined state, when it's just potassium on its own, it is of course 0. But when it is in its ionic state, it is +1. That's for group 1 elements. And also in group 2 elements, the ions oxidation number is +2. So for example, magnesium, which is a member of group 2 elements on the periodic table, when you have magnesium ion, the oxidation number for magnesium ion is +2. For magnesium in its uncombined state, for the magnesium atom, it is, of course, 0. But in its ionic state, for group 1 elements, the oxidation number is +1. For group 2 elements, the oxidation number is +2. And then there is the zero-sum rule, which we've touched upon in the previous slide, is that the sum of all the oxidation numbers in an electrically neutral compound must equal 0. So if you recall our carbon dioxide example in our previous slide, carbon dioxide is neutral. It's a neutral compound. It doesn't have any overall charge. It's not an ionic compound. It's overall, its charge is neutral. So the sum of the oxidation numbers for carbon dioxide has also got to add up to 0. In another example is H2O, this water molecule. H2O is neutral. It doesn't have any charge. So you can see that for hydrogen, the oxidation number is +1. If you recall, the oxidation number for hydrogen in most compounds is +1, except for these metal hydrides. So +1 for the hydrogen, and we have 2 of them, H2, so 2 times +1, plus for oxygen, it's -2. Plus a -2. And as you notice, these do add up to be 0. And that's called the zero-sum rule. The sum of the oxidation number in an electrically neutral compound must equal 0. And then the last rule is the ion charge rule. So the sum of the oxidation numbers in a polyatomic ion must equal the overall charge of the ion. So for example, if you have an ionic, an ion, a polyatomic ion, such as this nitrate or such as this hydroxide molecule. So if you notice, this hydroxide molecule has an overall charge of -1. So when you add the oxidation numbers for oxygen and hydrogen, they have to add up not to 0, but to the charge of that ion. So in this case, the hydroxide ion has a charge of -1. So when you take the oxidation number for oxygen, which is -2, and you add the oxidation number for hydrogen, which is +1, and you add these, you notice they will result in what is the overall charge of this hydroxide ion in -1. And just finishing this example with the nitrate ion, again, it seems this nitrate ion has an overall charge of -1. So knowing that we have to end up with a charge of -1, and we see that oxygen, we have 3 of them. Oxygen has to have an oxidation number of -2. And since we have 3 of them, 3 times -2. And then we have 1 of the nitrogen. What does the oxidation number for the nitrogen need to be? Well, it needs to be a number that once added to this 3 times -2, so -6, will result in -1. So this has got to be a 5. In this case, nitrogen has an oxidation number of +5. So +5 minus 6 is equal to -1. So that's the ion charge rule. So if you practice with applying these rules to a few examples, you really start to get a hang of it, and then you can pretty much figure out the oxidation numbers and assign oxidation numbers to really any molecule. So let's look at an example. Here, we're determining the oxidation number of the nitrogen in the molecule lithium nitrate. Okay. So the first step is that we write down all of our known oxidation numbers. So we have lithium, we have nitrogen, and then we have oxygen, 3 of them. So the lithium, it's got a charge of +1. We know that because it's from the group 1 elements of the periodic table. Oxygen, we know that it always has an oxidation number of -2, unless it is, if you recall, unless it is in hydrogen peroxide in H2O2, then it's going to have an oxidation of number 1. So in this case, in this molecule, it will have an oxidation of -2. What we don't know is we don't know what is the oxidation number for nitrogen in this molecule. And sometimes the oxidation number for nitrogen might be different depending on what compound it occurs in. So let's find out. So overall, this lithium nitrate has got a charge of what? What kind of a charge does this lithium nitrate have? Does it have any charge on it, or is it neutral? Is there no charge on it? It's electrically neutral. Anybody want to answer that question? Does lithium nitrate have a charge? What do you guys think?
I can say again.
So does lithium nitrate have a charge on it? Do we see any minuses or pluses up here? Is it lithium nitrate -1 or +2?
No.
No, it doesn't. It is neutral. It has an overall charge of nothing. So overall, when we add all of these oxidation numbers, it has to add up to 0 because there is no charge on this molecule. Remember, if this molecule was something like a nitrate molecule or a hydroxide molecule, something that has a charge on it, a -1, for example, here, or I don't know, a +2 or what have you, then it has a charge on it. But in this case, lithium nitrate is neutral. There's no charge on it. So all the oxidation numbers, once you add them up, have to add up to be neutral, to be 0. So let's try and figure out what is X? What is the oxidation number for our nitrogen? Well, we know for lithium, we said it's +1 because it's a member of the group 1 elements of the periodic table, and group 1 elements have an oxidation number of +1. That was from our table. We learned that from our table, that group 1 elements, ions, have +1. Okay, so there it is. And then we have this nitrogen we're trying to figure out, then oxygen. Oxygen always has a charge of an oxidation number of -2. And since we have 3 of them, we multiply this number by 3. So all of these numbers added together, we can write an equation for it like this, and write that it should equal to 0. And then we can solve for X and figure out that X is equal to +5. So the oxidation number for nitrogen in this molecule of lithium nitrate is +5. And there are some more support questions here for you guys to practice with. In this one, you're asked to assign the oxidation numbers to each atom in each one of these. So figure out what is the oxidation number for nickel, what is the oxidation number for chlorine in this molecule of nickel chloride? What is the oxidation number for this magnesium atom? What is the oxidation number for this one? What is the oxidation number here? So assign it for each one of the components, each one of the atoms here in these molecules. In number 3, you're asked to assign oxidation numbers to the underlined atoms. So figure out what's the oxidation number for the chlorine here. What's the oxidation number for chromium? What's the oxidation number for tin? What's the oxidation number what is a gold, I guess. So yeah, you have to figure out what they are. And assign these oxidation numbers to the elements for this question as well. And then finally, in this question, you're asked to assign the oxidation number for the atoms in molybdenum disulfide. So try all of these. It'll give you good practice to figure out how to assign oxidation numbers. So how do you figure out whether a reaction that you're looking at is a redox reaction or is it not? So it will be very useful to figure out if a reaction is redox reaction or not. In order for a redox reaction to have occurred, what needs to have happened? There must be a change in the oxidation number. So either the oxidation number has decreased or the oxidation number has increased. If the number has decreased, then you know that there's been a reduction. If the oxidation number has increased, you know that there has been an oxidation. So in this example, sorry, where was I? So in this example, you're asked to determine if the reaction is a redox reaction, as a redox reaction occurred. So in these two equations, all right. So let's look at how we would look at the equation in A. So the first step is to write down all of the known oxidation numbers. So based on the rules that we are going to familiarize ourselves with in that table, write down all the oxidation numbers that you know right away. So we know that any elements in their lone state here by themselves are going to have an oxidation number of 0. So let's refer back to that table. So if you remember, all of these kinds of elements, when they're uncombined and just in their state by themselves, in their uncombined state, they will have an oxidation number of 0. So here, zinc is going to have an oxidation number of 0. Sulfur here, again, is also in its uncombined state. It's not combined with any other atoms. So it is also going to have an oxidation number of 0. Now in this zinc sulfide compound, zinc being a member of the group 2 elements, it is going to have a +2 charge. So it's going to be +2. And since overall this molecule is electrically neutral, the sulfur is going to have -2 charge. So here we can see that the zinc has changed from an oxidation number of 0 to an oxidation number of +2. Zinc has changed oxidation numbers from 0 to +2. Sulfur has changed from 0 to -2. Therefore, this is a redox reaction. Okay, this is a redox reaction. Now let's look at the next one, this equation in B. So again, first we write it all out, we space it all out. We kind of, it's the same reaction we have up here, but if you notice, we've just kind of stretched everything out and spaced it all out. We've left all the space underneath it to allow ourselves to write these numbers without getting too crowded and too messy. So it's that same equation, but just write it putting like lots of space in between all the different atoms, right? So SO3 is here, but you just put a lot of space in there so that you can make it nice and neat. H2O is here, but you just leave a lot of space between the H2 and the O part so that you can write these numbers neatly. Same with the H2SO4, just space it out, stretch it out so that you have room to write down your oxidation numbers. So sulfur, we don't know. It didn't follow any of those rules that we've become familiar with on our rules table. Oxygen, we know. Oxygen will have -2, right? And we've got 3 of them. So 3 times -2. The hydrogen in H2O, we know it's going to have a charge of +1, and we've got 2 of them. So we write down 2 times +1. Oxygen in this H2O is going to have an oxidation number of -2 because oxygen always has an oxidation number of -2 unless it's part of hydrogen peroxide. And then we come to this H2SO4, this sulfuric acid here. We look at the hydrogen. Yes, we know hydrogen is a +1. We've got 2 of them, so we write 2 times +1. Sulfur, we don't know what's the oxidation number, but we can figure it out. Oxygen, again, is -2. We have 4 of them, so we write 4 times -2. Then we're going to apply that rule of, let's go back to our table and see that there is the zero-sum rule. The sum of the oxidation numbers in an electrically neutral compound must be 0. So this SO3 molecule that we have here, right, SO3, we don't see any charge on it. It's electrically neutral, right? Same with this H2O. This H2O is electrically neutral. And same with this. So we know that the number of electrons from on this side have to be the same as the number of electrons on this side. Whatever was gained has to balance out with whatever was lost. So this, this X plus this -6 plus this +2 plus this -2 all together have to add up to 0 because all of these are electrically neutral. There's no charge on them. They're all 0. So once you add it all up, you see that X is equal to +6. Same with the H2SO4. We add it all up and we see that H2SO4 is an electrically neutral compound. There's no charge on it. So it has to add up to 0. And once we add it up to 0, we see that X is equal to +6 again on this side as well. And since we see that there is no change in oxidation number for any of the atoms here in this reaction. So if we look and see, we see that oxygen is a -2 on before the reaction, and it's still -2 after the reaction. Hydrogen is +1 before the reaction, and it's also +1 after the reaction. It's the same number as in the reactants as in the products. And even sulfur. Sulfur is +6 in the reactants and is +6 in the products. There is no change in this case in the oxidation number for any of these atoms, not for sulfur, not for oxygen, and not for hydrogen. So therefore, this one is not a redox reaction. So by figuring out what is the oxidation numbers, if you notice that there is no change, then this is not a redox reaction, okay? Again, there's a few support questions for you guys to practice with and to show that you really understand what is a redox reactions and which one are not a redox reactions. Then we have to look at how do we balance redox reactions. So if you've got a very simple type of redox reaction, you can balance it just by inspection, by just looking at it and examining the numbers on either side, or by inspection or by trial and error. But if you've got a more complicated type of redox reaction, then it's going to be very difficult to balance it just by inspection or just by trial and error. You're going to be spending a lot of times and doing a lot of trial and error before you do that. And it's better to have a systematic method of balancing more complex redox equations, redox reactions. So you can use half reactions to balance these redox equations. And one method is called the oxidation number method. And the increase in oxidation number for an atom or an ion must be equal to the decrease in the oxidation number of another atom or an ion. So, and that's the approach you're going to use to balance your redox reaction. If we want to think about it in more simple terms, the increase and then the subsequent decrease in the oxidation number must be the same. So let's look at an example to understand what we mean by this oxidation number method. Here in example 4, you're asked to balance this redox equation using the oxidation number method. And you're told to be sure to check that the atoms and the charge are balanced. Okay, so let's take a look at how we are going to do this. So first of all, write out your equation. And your first step is to verify that this is indeed a redox reaction. So as you write down the oxidation numbers that you know, you fill them in for all the ones that you do know, and you write X or Y, for example, in the ones that you don't know. And then you go and you apply the rules that you know about whether something is electrically neutral. So all the oxidation numbers have to add up to 0. So by doing that, you can figure out that in this molecule of HNO3, H, you know, has an oxidation number of +1. Oxygen, you know, has an oxidation number of -2. You have 3 of them, so you multiply it by 3. Nitrogen is not one of the ones that we know the oxidation number of, so we have to do some math to try and figure out what is the oxidation number for nitrogen in this HNO3 molecule. And by doing the math, we see that the oxidation number for the nitrogen in HNO3 is +5. Then we go to the next molecule. And we figure out that there is 3 hydrogens there, and those have an oxidation number of +1. 3 oxygens, oxidation number of -2. We write an unknown for the atom that we don't know the oxidation of, and we do the math and we figured out that it's an oxidation number of +3. So then same for the reactant side. We don't know what is the oxidation number for this N here. We know that for oxygen, it's -2. And since overall there is no charge, so If this is -2, this has got to be +2. So for this one, nitrogen has an oxidation number of +2. And if you notice, it's entirely possible for nitrogen to be +5 in one, have an oxidation number of +5 in one compound, and an oxidation number of +2 in a different compound. Same as here, you do that same approach and you figure out that overall, this one has an oxidation number of +5. So therefore, since this nitrogen has changed from +5 to +2 on the product side, it's been reduced. And AS has changed from +3 to +5, and so it's been oxidized. Therefore, because there is a change in the oxidation numbers, therefore this is a redox reaction. So first step, we've determined, are we even looking at a redox reaction? Okay, yes, we are looking at a redox reaction. Then step 2 is to determine the net increase in oxidation number for the element that is oxidized and the net decrease in oxidation number for the element that is reduced. Remember, when an element is oxidized, you get an increase in its oxidation number. It's oxidized, so you get a bigger oxidation number. And when it's reduced, just like the word says, you get a decrease or a reduction in its oxidation number because it's reduced. So for AS, it's from +3 to +5, and that is a net change of +2, or sorry, a net change of -2. Or no, it's where are we looking? AS 3 to 5. Yes, it's a change of +2 because for 3 to 5, it's +2. And for nitrogen, it's from 5 to +2. So it's overall the net change of -3. To go from 5 to 2, you have to subtract 3. So a net change of -3. Then we have to, the next step is to determine the ratio of our oxidized to our reduced atoms. That would give us the net increase in the oxidation number that is equal to the net decrease in the oxidation number. What do we mean by that? We mean that 3 atoms of AS would yield a net increase in the oxidation number of +6. So 6 electrons would be lost by 3 of these atoms. But 2 atoms of N would yield a net decrease in oxidation number of -6. So 6 electrons would be gained by 2 Ns. So you would have a ratio of 3 to 2 for these 2 atoms. So in step 4, to obtain the ratio that you identified in this step 3, you add the coefficient to the formulas which contain the elements whose oxidation number is changing. So these coefficients we add to the elements whose oxidation number is changing. So we put down the 2 over 3 here, and we put down the 3 over here, right? Because that's where there is that AS, and the 2 is where the N is here. So 2 here and 3 here. And then once we have those 2 in place, the rest of it, then we can go ahead and balance by inspection. So we just look and we count up all of our elements and make sure we have as many on this side as on this side. Okay, so, and then we notice that if we put a 2 here and a 3 here, then it all balances out. So the rest you can just do by inspection. Now, In some of these redox reactions, they may occur in an acidic or in a basic solutions. How do we balance those types of equations? Where the steps to balancing a redox reaction that occurs in an acidic or a basic solution is a little bit different, meaning that you may need to add water molecules or hydrogen ions or hydroxide ions to balance out your equation. So let's look at one example here. And you're told that this chlorate ions and this iodine are reacting in an acidic solution. So you're told that this is happening in an acidic solution to produce these chloride ions and these iodate ions. And so some of the steps here will combine some of the steps that we used in our previous example, just so that our solution is not very, very long. So you can apply some of the steps from before. So steps 1 and 2, you determine if the reaction is a redox reaction and what is the net change in your oxidation numbers. So by doing just the kind of steps we did in our previous example, we'll see that there is a reduction of the chlorine from a +5 on the reactant side. So once we figure out all the oxidation numbers and we apply them, we'll see that this chlorine on this side, on the reactant side, has got an oxidation number of +5, but on the reactant side, it has an oxidation number of -1. And so the net change here is -6. And then for the oxidation half reaction, we see that the iodine, which started on the reactant side with an oxidation number of 0, on the reactant side has an oxidation number of +5. So the net change is +5. So there is a redox reaction going on. So the next step is to determine what is the ratio of our oxidized to our reduced atoms that would yield the net increase in the oxidation number equal to the net decrease in the oxidation number. And this is just simply just ratios and math. That's all it is. So here you see that if you have 5 chlorine atoms, they would yield a net decrease in oxidation number of -30. And if you have 6 iodine atoms, you would have a net increase of +30. So essentially, you're trying to find what is the common number linking 6 and 5 together. So just by looking at this very mathematically, what is a number that you can, that is a factor of 6 and 5? Well, that number has to be 30. So if you have 5 chlorine atoms, remember chlorine had a net change of 6. So 5 of those -6s, so 5 times -6, you would get -30. And then the iodine was a net change of +5. So if you have 6 of those, 6 times +5, you would get a net change of +30. So -30 +30, perfect. So to obtain the ratio that we identified here in this previous step, we add the coefficients to the formulas, which contain the elements whose oxidation number is changing. So we add the those coefficients of 5 chlorine and 6 iodine to the reactant side, where the elements where the oxidation number is changing. So here we add 5 in front of the chlorine, and we would add 6 for the iodine. But notice that there are 2 iodine molecules. So here, so in this case, there are 5 electrons per iodine molecule, right? Because it's got a net change of +5. So 6 times 5 electrons, 30 electrons. and 10 electrons per iodine molecules in the I2 state. So 3 times the 10 electrons would be 30 electrons. So we make sure to put 3 in front of here, and that's how it balances itself out. And 5 over here and 6 over here. So notice that although the chlorine and the iodine is balanced, now what happens? The oxygen is not in this reaction. And since the reaction occurs in an aqueous solution, notice all these aqueous symbols here down at the bottom. That means in water. So we can add water to balance out the oxygen atoms. So in this case, the reactant side is short 3 oxygens. 3 oxygen atoms. So we add 3 water molecules on the reactant side in order to balance this. So we can add 3 molecules on this side. Then we have to add hydrogen ions now to balance the hydrogen atoms, because now by adding 3 water molecules on this side, now we have added hydrogen atoms to the reactant side. We need to have hydrogen atoms in the product side. And because this is happening in an acidic solution, so there's going to be always extra hydrogen ions around. So we need to add enough hydrogen ions on this side of the reaction in order to balance the whole thing out. And that is the steps for balancing a redox reaction that takes place in an acidic solution. Okay, now it's a lot, but go through it step by step. Make sure you understand, and you can do all of these steps and it all makes sense to you. It'll take some time to digest and to understand, but just follow through and understand that there is some math involved here. So just look at the numbers and see what are the common factors, and you shouldn't have any problem going through it. In our next example, what if this was in a basic solution? So the first example we did was in an acidic solution. In our next example, it's in a basic solution, right? So that was acidic solution. This is the basic solution. And I'm going to underline this just to make sure everybody pays attention to how these 2 examples are different. The first one was in an acidic solution. Next one is in a basic solution. And the method that you apply in a basic solution is just a little bit different. So let's go through this example as well in a basic solution to make sure we've all got a hang of it. So here you're given this equation of this methanol reacting with this permanganate ion in a basic solution. And the reactant and the product of this equation are shown for you. And so you have to balance this equation. You're asked to balance this equation. How do you balance this type of an equation that is happening in a basic solution? So again, our first step is to determine is this even a redox reaction? So we use our methods for determining oxidation numbers. And we first start out with the oxidation numbers for the ones we know, we write it out, and then we figure out oxidation numbers for the ones that we don't know, such as the carbon and the manganese. And by doing that, that process, we see that carbon on the reactant side has got an oxidation number of -2. On the reactant side is -2. On the product side, it is +4. Okay. For manganese, on the reactant side, it would be a +7 oxidation number once we figure it out. And on the product side, it is a +6. So the net change going from a -2 number to a +4 number is, of course, plus 6. You have to add 6 to minus 2 to arrive at plus 4. And to arrive from plus 7 to plus 6, you have to subtract 1. The net change is minus 1. So if we figure out what would be the net change here, what would be the net change there. So then, because there is a net change in the oxidation numbers, this is a redox reaction. Yes, it is. In step 2, you have to determine the ratio of these oxidized to reduced atoms. That would give us a net increase in oxidation number equal to the net decrease in our oxidation number. So here we have 1 carbon atom would yield a net increase of 6 electrons, right? And you would have 6 manganese atoms that would give a net decrease of 6 electrons. And so to obtain this ratio that we figured out in step 2, you have to add these coefficients to the formulas which contain the elements whose oxidation numbers are changing. So here, the oxidation number of a manganese and the oxidation number of the carbon are changing. So you add the coefficients here and here. And then you would have to, and of course for carbon, it's just a coefficient of 1, you don't have to add it. And here you, in step 4, you see that you still need to balance out the number of oxygen atoms. So for the oxygen atoms to balance out, you add water. So you notice that you have to add water to this side of the equation to make up for the number of oxygens that are on this side of the equation. And that involves adding 2 H2O molecules, because on this side, we need 2 more oxygen atoms to balance out the number of oxygens on that side. And now, because we've added water, water doesn't just bring along with it the oxygen, it also brings along with it the hydrogens. So now we would have to add some protons to the other side to balance out the number of hydrogens. So we add the water, then we balance it out by adding hydrogen atoms. Then we say, well, this is in a basic solution, so we have to add enough OH molecules to the reaction to equal the number of protons that was present, which in this case was 8. So if we add 8 OH molecules to this side and 8 OH molecules to that side, we'll see that these two together will react and become H2O, 8 H2O molecules. On this side, we have 2 H2O molecules. So 2 from this side and knock down 2 from this 8, you're left with 6 H2O molecules. And of course, the 8 hydroxide ions that we added on this side. So canceling out the water on both sides, the 2 from that side and the 8 minus 2, you're left with 6. This is the final balanced equation for that reaction, that redox reaction, taking place in a basic solution. Again, I understand it's a lot of steps, but this is the order of steps that you have to follow in order to balance equations, these redox equations, in a basic solution, or in this case, in an acidic solution. If you notice, there's a slight difference in the last few steps between the two. Okay. Then there are some support questions for you guys to practice with, and it would be very beneficial for you to do practice with these support questions. It would help you tremendously. Then there is another method for balancing redox equations. So that was the oxidation number method. Right. So that was the oxidation number method, using the oxidation numbers method. There's a second method called the half reaction method. And in this half reaction method, you start by looking at the half reactions, and the electrons of these half reactions then have to be balanced. So for balancing these half reactions in an acidic solutions, these would be your steps to follow. And for balancing these half reactions in basic solution, these would be the steps to follow. So let's just quickly go through these few points, and then we can look at some examples of how to do this for an acidic, in an acidic solution, in a basic solution, using this half reactions method. So if you're balancing half reactions in an acidic solution, first thing to do is to write out the half reactions, unbalanced. Just write out those half reactions. So the oxidation half reactions and the reduction half reactions. Then you have to balance any of the atoms other than oxygen and hydrogen. So which is actually what makes sense to do even from our previous example. First, you want to balance the atoms other than oxygen, other than hydrogen. Then you want to balance any oxygen atoms by adding water molecules. Then you want to balance any hydrogen atoms that came from the addition of that water molecules by adding hydrogen ions. Then you want to balance the electron charges of that half reactions. And then you want to add the half cell reactions together, and that will give you the final balanced equation for that reaction in an acidic solution. Now, if you're doing this half reaction method in a basic solution, you basically follow the same procedure as you did for the acidic solution, but then you adjust for your basic solution by adding to both sides the same number of hydroxide ions, kind of like we did in our previous examples as well. We added hydroxide ions to both sides, and to balance out your number of hydrogen ions that you've already got present. And then you simplify the half reaction by combining the H's and the OH minus to form your H2Os. And then you cancel out whatever extra H2Os you have on either side of the half reaction. And finally, you balance the charges by adding any electrons as needed. And then you add your half cell reactions together. But note that once the oxidation half reaction and the reduction half reaction are balanced independently, they can be combined using the lowest common multiple of the number of electrons. So whatever is the lowest number of electrons that's common between them, you can add your two half reactions. You can combine them in that way. So let's look at two examples. The first one being using this half reaction method in an acidic solution. So here you have an equation of iron ions being added to dichromate ions. And you have reactants and you have products. It's being indicated that this is taking place in an acidic solution, and you are asked to balance this equation. And again, this is not a simple equation that you can just visually do, so you have to go through those prescribed steps. So using the half reaction method, which is what is being asked in this question, using the half reaction method, you write out your half reaction. So the first half reaction is, okay, so your Fe+2 ion, the iron 2 ion, goes to iron 3. And then you have your dichromate ion goes to your chromite ion. Now for the iron 2 half reaction, you just need to add electrons to balance the charge, right? It's pretty simple. It's pretty straightforward. How do you go from this Fe with a charge of 2 plus to Fe with a charge of 3 plus? Well, you have to lose one more electron from here to drop your charge to be, to raise your charge to be even more positive. So it would be Fe2 plus goes to Fe3 plus an electron. So you have to add an electron to this side, and that balances out the charge, no problem. Now for the dichromate half reaction here, it's a little bit more involved. So first you balance the amount of oxygen that you have by adding water molecules, and then you balance the hydrogen atoms with hydrogen ions, and then you finally balance the electrons with charges. So here in this case, first of all, the first step was to balance out all the atoms that are not oxygen. So this chromium here, you see, you've got 2 of them here, Cr2, and you've got only 1 here. So if you put 2 on this side, then that balances the chromium part, right? Then you start adding, you start to balance out the oxygen by adding water. So you see that, okay, you have 7 oxygens on this side and no oxygens on this side. Well, let's balance that out. So we start by adding 7 H2Os with this side. That's our first step, 7 H2Os. So now we've got 7 H2Os, so 7 oxygens and 7 oxygens. We're good with oxygens. Then we want to balance out our hydrogens, because look, now we've introduced hydrogens to this side of the equation. How many of them? Well, 7 times H2, so 14 hydrogens have been put on this side of the equation. And since this is in an acidic solution, go ahead and add 14 protons to this side of the equation, 14 H pluses to this side of the equation. So now we've got our chromiums balanced. We've got our oxygen atoms balanced. We've got a number of hydrogens balanced. What we're left with now, we need to make sure that our charge is balanced by adding electrons. So if we look at what is the charge on this side and compare it to that side, we see that we need to have 6 electrons put in place here. Okay, and if we add up our 6 electrons, our -6 and a +14 charge, and our -2 charge here will end up with a +6 charge on this side overall. And on this side, our electron charges, this one is 2 times +3, so we have +6, plus for the H2O, it's 0. So it would be +6. So now we see that our charges are now balanced by adding these 6 electrons here, this -6 here. So now we have to see, to balance these equation, we have to multiply either one or both of these half reactions. So here we have one half reaction and the other half reaction. So we would have to multiply either one or both of these half reactions now to balance the electron charges. So in this case, here we have just 1 electron. Here we have 6 electrons. So if we add these 2 together, we'll have 6 on this side, 1 on this side. In order to balance this, we'll see that in this case, the iron half reaction, if you multiply it by 6, you will end up with the right number of electrons. You'll end up with 6 electrons. So multiplying the iron half reaction, this was the iron half reaction, by 6. So now it's 6 iron plus 2 going to 6 iron 3s plus 6 electrons. Now, if we add these two half reactions, this one and this one, if we combine them together, we'll see that, okay, so now these 6 electrons can cancel each other out, and we are left with this as our final balanced redox reaction in an acidic solution using the half reaction method. Okay. I know it's a lot to go through. I'm just hoping that I've explained things clearly, and that if you need to, we are recording this. So you can go ahead and listen to this lesson again and also practice again on your own time with these examples and also the support questions, and ask if anything is confusing, if you feel like there's an example that you'd like to go through together, if there's a support question that you feel like we should do together next class, let me know, because I will be expecting you guys to know how to do these things, and this might come up in some form or another on the final exam. So make sure you understand how to do these balancing of redox equations in acidic solution and basic solution, whichever. That being said, now let's look at an example of how to balance a redox equation in a basic solution using the half reaction method. So here, again, we have methanol reacting with permanganate in a basic solution. So this was, I think actually it's the same example as before, but we're just going to balance it using a different, this new method. So you're being asked to first write the balanced half reaction equations for this reaction, and B, write the overall balanced equation for this reaction. So the first thing we do is we figure out the two half reactions and we split them apart. So here we pull out the methanol and this carbon trioxide here. And we just balance it out, the half equation for this using those steps. And the same for the permanganate ion. We balance it out separately, okay? And then it says to write the overall balanced equation for the reaction. So here are the balanced half reactions using those steps that we discussed here. So go ahead and go through these steps and see, are you able on your own to come to this point? Okay, so go ahead and practice starting from here and see, can you arrive to this point? And then from here, can you do B? Can you determine what is the overall balanced equation for this reaction? So if, now for B, you would have to determine what is the whole number that will balance out the number of electrons transferred for each of the reactants. So in this case, there's 6 electrons here. There's 1 electron here. How do we balance it out? Well, we would have to multiply this whole thing by 6 in order to have 6 electrons on this side and 6 electrons on that side. So multiply the whole thing by 6 times. So if we do that, we end up with this reaction. And now if we add these two half reactions, this one and the oxidation one, the oxidation and the reduction one, then we get this as our final balanced equation, because our 6 electrons will cancel each other out, right? and you'll end up with this overall balanced equation. So I really encourage you to try and see if you can follow these steps and arrive here. And then, of course, the support questions are really important to practice with. And finally, we have our key questions. So these key questions key question number 13, which is this lesson, is due, I'm sorry, this is the wrong date. This is due this Sunday, November 7th. So let me just update that for you. November 7th. And also the activity series of metals from lesson 14, that is also due this Sunday. This is the independent study unit. And the key questions for question number 14 for the activity series of metal, although you don't have to hand it in, you do have to go through this and understand this. And actually, if we have some time, maybe perhaps I can start you guys on that even today. But the assignment is a bonus mark assignment. So if you decide to hand it in, it's due by Sunday, and it would count as a bonus mark towards removing your lowest mark at the end. Okay, so I urge you guys to do key question number 13 and go ahead and do key question number 14, even though it's a bonus, do it. It's good practice, hand it in, get those bonus marks. Do whatever you can to improve your marks at towards the end of the course, okay? We're kind of getting close there. We are in our second last unit for the course. Okay, since we're still here and we still have half an hour of our lesson left to go, we can go through this activity series of metals, lesson 14 together, since we have time. I'm just gonna open it up. Oh, before we do that, any questions about what we covered here today? Everybody thinks they understand it well enough to be able to go home and to not go home, but at home on your own time, be able to go through this and figure this out.
I think I got it. Yeah.
Yeah, you think you're okay, Borna? Okay, that's great. Judy, Sasan, do you guys have any questions from for lesson?
Oh, I'm Sasan, not Born.
Oh, I'm sorry. You know, your voice sounded exactly like Sasan, but for some reason on my screen, I thought I saw Borna's mic moving. I apologize.
Yeah, it wasn't me.
Yeah, that's strange. I saw your mic moving. Okay. So we have, so yeah, if you guys feel like you're okay with the contents of lesson 13, and these oxidation reduction reactions, then I'm just gonna go ahead and go through lesson 14 with you, even though lesson 14 was an independent study unit. But since we went through lesson 13 so quickly, we still have half an hour. And lesson 14, as you can see, is a very short little bit of a lesson, and we can go through this together. And then you guys should spend some more time looking at it. And yeah. So here we're going to talk about the activity series of metals. And what we mean by activity series is that metals tend to react by losing electrons. And some metals will lose electrons more readily than others. And this will be indicative of how reactive a metal is. And how reactive a metal is helps chemists to predict whether a reaction will occur, whether that reaction will occur spontaneously or not. So in this lesson, we're going to be talking about a ranking chart for metals that is used in chemistry, and this is called the activity series of metals. It's a way of ranking metals on a chart, on a table, to see which ones will lose electrons more readily and which ones will react more spontaneously. And by doing this, we'll learn to predict the spontaneity of various reactions using this activity series. And okay, let's jump right in. Let's talk about conductors versus non-conductors. A conductor is something that is capable of conducting electricity, whereas a non-conductor, as you can imagine, is something that then does not conduct electricity. So if you can think of the human body is mostly water, and it's a relatively good conductor of electricity. For this reason, we have to be careful when we're using electrical devices around water when the conditions are wet. But you may be surprised to know that if you have pure distilled water with absolutely no other ions, no other impurities in it, pure distilled water does not conduct electricity. It is the ions that are present in water, those impurities, those ions that are present, any salts, any other molecules, those are what will allow for the flow of electrons or electricity in water. And human blood is mostly water and dissolved ions, and that allows for a very good flow of electrons and a good conduction of electricity. So generally, substances that can be ionized are conductors. For example, things like acids and bases. You can have acidic ions. For example, this sulfuric acid can ionize into 2 hydrogen ions and a sulfate ion. You could have basic ions. This calcium hydroxide can ionize into a calcium ion and 2 hydroxide ions. And you can have salt ions. The sodium chloride will ionize into a sodium ion and chloride ion. And then in addition to these chemicals that can ionize, metals are good conductors of electricity. And the reason these metals conduct electricity, if you can think back to our lesson that we covered metallic solids, if you remember, metals conduct electricity by passing charge through this pool of electron, this electron pool of just free-floating sea of electrons, I believe was the term that we used in that lesson, this free-moving sea of electrons. So these electrons move freely in this sea of positive ions in the metals. So that is why metallic solids, metals, are good conductors of electricity, because they have these freely moving electrons. These electrons aren't necessarily associated with any single nucleus, but are very much free flowing among this sea of positive metal ions. So ionic metals also ionize to conduct electricity, and though in that case they are termed electrolytes. And it's important to know that these ionic compounds only conduct electricity when they are in their aqueous ionized form. So if you have this solid sodium nitrate, when it's solid, when it's dry, it's not a conductor of electricity, whereas in its aqueous form, these ions of sodium and nitrate, these, once they're dissolved in water and are in their aqueous form, are excellent conductors of electricity. Non-conductors or non-electrolytes are then the substances that don't ionize. And these examples are examples that like alcohol does not ionize. Sugar, it does not ionize. It doesn't become any kind of an ion with any kind of a charge once it's in water. Pure water, pure distilled water does not ionize. Covalent molecules do not ionize. So it's these ionic compounds that, that ionize, such as this sodium nitrate or calcium hydroxide. These are the type of molecules, calcium chloride, these are the ones that will ionize. So let's look at an example. So here in this example, you're asked to determine if of this list here, these substances, which ones would be conductors of electricity in the form shown. So pay attention to whether it's aqueous or solid or liquid. So pay attention to the state. So which one of these can conduct electricity in the form that it's shown, in the state that it's shown? So the first one, this copper chloride, aqueous. Copper chloride would be a conductor. And this is because this is an aqueous ionic compound. You can see that it's aqueous. So it will, in solution, you will get copper plus 2 ions and Cl minus chlorine ions. So that one would be a conductor. Now, solid NaOH, solid sodium hydroxide, solid, would be a non-conductor. This is a solid ionic compound. It is ionic, but because it's solid, it is not ionized. So it would be a non-conductor. Water, as we said, is a non-conductor. Pure distilled water has no ions, it has no impurities, it doesn't have anything in it except H2O. This is a non-conductor of electricity. It does not conduct electricity if you have pure, absolutely pure distilled water. Then you have methanol. Methanol is a non-conductor. It's a covalent compound. It's an alcohol. And covalent compounds are non-conductors. Finally, hydrogen chloride, aqueous. Hydrogen chloride is an aqueous acid, and as such, it will ionize into H plus and Cl minus, aqueous, and aqueous acids are conductors. So this is a conductor of electricity. Support questions for you guys to practice with. Now let's get into the actual activity series for metals. So thinking about why is it that expensive jewelry is made out of expensive metals such as gold? Well, that's because gold is one of those metals that it doesn't seem to tarnish. It doesn't develop a tarnish on top of it. It doesn't rust. It doesn't oxidize the way, for example, silver can. It doesn't oxidize the way copper can. So often, if you have costume jewelry, the cheaper jewelry, you will find that there is tarnish and change of color on the metal parts over time. And electrochemistry, we can use electrochemistry to explain why some metals tend to react more readily and be more reactive and tarnish, whereas other ones are less so. Other ones don't. So an activity series, if you recall, is the list of substances that are then ranked in the order of their relative reactivity. That's the activity series for metals. For example, you can have magnesium metal, and magnesium metal can displace hydrogen ions out of solutions. So it is considered more reactive than hydrogen. So let's look at this reaction here. Magnesium atoms, solid magnesium, plus protons in the aqueous solution. And I'm sorry, I'm missing my arrow here. It displays, so it forms hydrogen gas and magnesium. So magnesium can displace these hydrogen ions out of solution. So it can push them from being aqueous protons to bubbling out of solution in the form of hydrogen gas. So magnesium is considered to be more reactive than hydrogen metal because it can displace these hydrogen atoms out of solution. Displace means to move them, to change their place, to going out of solution. Zinc is another example. Zinc and hydrogen ions. Zinc can also displace these hydrogen ions out of solution. Zinc can also push these aqueous protons, these aqueous hydrogen atoms, to bubble out of solution in the form of hydrogen gas. This means that zinc is also more active than hydrogen. But for example, a metal like magnesium, magnesium can remove zinc ions from solution. So if you have magnesium, solid magnesium atom, and you have zinc ions that are in solution, zinc in its aqueous form in solution, magnesium can then displace those zinc ions from solution and cause them to come out of solution in the form of zinc atoms, in the form of metal, metallic zinc, and then the magnesium itself will go into solution. So here, magnesium is more active than zinc because it can displace zinc ions out of solution. And the activity series includes these elements in the order of their activity, as magnesium being more active than zinc, being more active than hydrogen. And the activity series, which we're going to look at on the next table, was made in a very similar way by doing experiments and determining the order of reactivity of metals with respect to each other. So most of these active metals are then on the top of the table, and the least active metals are the ones on the bottom of the table. And each metal is then able to displace the element below it out of solution, or by using the right language for electrochemistry, each metal can reduce the cations of the metals below it to their elemental form. So if you can see this way, magnesium was able to reduce these zinc cations to its elemental form. It can displace it out of solution in its elemental form. So let's take a look at that activity series table. Here it is. So these are the atoms that are most reactive, that are most easily oxidized. And we can use, and down here are the ones that are least oxidized, meaning not easily oxidized. And if you can see, hydrogen, which is starred right here, is the only non-metal that is included in this metallic activity series. This activity series of metals includes hydrogen. And you might be wondering why, and I urge you to go and find out why. You can use this activity series to then predict the product of a single displacement reaction. For example, you may have some general reaction, A plus BC goes to AC plus B. And in this example, the element A, as you can see, is displacing B, right? It's pushing B out to form AC. Itself is getting in there with C and is pushing B out. It's displacing B. Displacing B out of solution to form AC. So the activity series can be used to determine if this displacement reaction will occur or not. So in general, an element that's higher in this activity series will be able to displace an element that is lower. And when an element is displaced, when an element displaces one of these lower elements, it is called a spontaneous reaction. So these being able to displace the ones that are lower happens spontaneously. So in our second example here, predict whether a chemical reaction will occur in each of the following reactions. So aluminum plus silver nitrate. Aluminum in its elemental form, in its solid aluminum form, solid state, plus silver nitrate in its aqueous state. Will a reaction occur or not? So in this reaction, we'll take a look. We have to look at the two metals, aluminum and silver. Let's look on the activity series and see who is higher than whom. So if we take a look here, we see that aluminum right there is higher than silver. Aluminum, where was it? Aluminum is higher than silver. Silver is down here. So aluminum is above silver, and therefore a reaction will occur. So the reaction that will occur is that this aluminum will displace this silver. So the silver will be displaced out of solution, and you will have elemental silver, solid silver, and you will get aluminum nitrate. So aluminum will displace silver away from nitrate, and itself will take this place of silver, and you will get aluminum nitrate and elemental silver. And of course, balanced, 3 to 3. The next example is the elemental copper plus iron sulfate in its aqueous state. Will a reaction occur? In this example, let's take a look. We have copper and we have iron. Let's take a look. Can copper displace iron? Let's look at the activity table. Let's look at the activity table. We have, where's copper? Copper and iron. Okay, so what do you guys think? Will a reaction occur or not? Can copper displace iron? Copper's over here, iron's up here. Can copper displace iron? Somebody take a chance, go for it. Do you think copper can displace iron? Copper is here and iron is up here. Would copper be able to displace iron out of solution?
No.
Thank you.
Wait, my mic was muted, sorry.
Oh, that's okay. You can give your answer too. What do you
I
think?
think it's no.
The answer is no. Yeah, because it's copper is lower than iron on the activity series. So copper will not be able to displace iron out of solution. Thank you so much for talking to me. Yes, in this example, copper is below iron in the activity series, therefore no reaction will occur. You'll get no reaction. Copper is just not able to bump out iron away from sulfate and take its place. No. It's not high enough in the activity series to be able to do that. Then you have just some support questions, just like the 2 examples that we looked at that you guys can practice with, just to get a feel for how do you interpret the activity table and the position of these metals with respect to each other. And if you want to do some further reading, your textbook, your Nelson 12th chemistry textbook is the perfect place to do it. You can look at these pages and the appendices and get some practice looking at activity series and the relative reactivity of metals with respect to each other. And finally, key question 14. Like I said, this one is a bonus one. If you don't hand it in, you don't get penalized. But if you do hand it in, you get bonus points. And at the end, if there's assignments that you didn't hand in or assignments that you handed in but got a lower mark compared to this one, well, this can be used to improve your mark. So I urge you, even though you don't have to hand it in, go ahead, do your best, hand it in and reap the rewards. Okay. And yeah, these are the type of questions. And remember, with these bonus assignments, you've got nothing to lose. Go ahead, try whatever marks you get, it's a bonus. All right, that brings us towards the end of our lessons. So we covered lesson 13 and we covered lesson 14, which was an independent study unit. I still think you should go through it and make sure you really understand and do these support questions and do these examples and make sure that you know how the activity series works, because although this is an independent study unit and the assignment for it is a bonus, I do expect you to understand this, and questions like this may creep up on the final exam. All right, guys, if you have any questions, I'm happy to answer them in the last few minutes of our 2-hour session together. Any questions?
No question.
No.
Okay, great. So, all right, then in that case, I wish you all a good night. Oh, before I actually go, I just really want to make sure, and I hope everybody is referring to all the material that I'm sharing with you on your Google Drive with you. So first of all of our recordings, I'm going to stop emailing the links to you, because I think a much better way of doing this, and I wish I'd just done this from day one, is just to, on this Google document here, I've put all the links to all the lessons as they come, okay? And all the recordings, the links are here. All you have to go is open this Google Doc, click on it, and here's the password. Just punch in the password and off you go. You can listen to the lessons again. So for example, today's lesson 13 and 14, I will be updating it right here. So you will have a link and a password here for it. So I just want to make sure everybody's
This is
aware.
a lot easier. Thank you.
Yes, I think so too. Thank you for being patient with me. I mean, I'm also learning ways of doing these lessons virtually and just finding better ways, more efficient ways of doing it. So yeah, this is much better. I'm just going to stop emailing you these links. Go to this page, get it, and that's how we're going to do it. And I also want to make sure everybody understands that the lesson notes for these units, so unit 1, unit 2, unit 3, 4 and 5 are all right here shared with you. So you can go ahead. For example, Unit 4, electrochemistry, we started it today. You can go ahead and look at all of these notes ahead of time and print them if you like ahead of time and be studying them. I don't see why there's any reason why you shouldn't do that. I think it's hopefully everybody's been doing that all along, but if you haven't, well, I guess it's never too late to start. So Unit 4, Unit 5, all of these unit lessons are here for you guys to download and print. And then one by one, I'm sharing with you these lessons as I go. So, so you can even look at my slides again and listen to my lessons again as many times as you wish by going and looking at the recordings sheet. So there's a lot of resources available to you. And of course, on the welcome doc, there is just reminders of what lessons are coming up, when things are due, whether questions are ones that you have the option of handing in, are they bonus or are they just regular assignments that have to be handed in. So all the information is over here. If you ever wonder what date is something due, what date is our lesson coming up, you can see right here, our next lesson is Wednesday, November 3rd on the galvanic cell. Okay. And oh, I actually just noticed that I might change the due dates for this. Yeah, I think I might change this to number 7 since I covered it today and I think it's fair. And then we can push these two for next week. We can push these two for the 14th. Okay, yeah, I think that'll work. Yeah, so, right. And I already changed the dates here. Yeah, all good. So yeah, all of these resources are available for you. All the information is available to you. And we have these 2 units to cover. As always, I try and make sure I put in a review session at the end of the unit to answer any questions. I really, really, really wish for you guys to use these review sessions as like a tutorial. Just ask me. I've been trying this question. I didn't get it. I'm having trouble with it. Or I listened to your lesson, but I didn't understand this part where you were explaining. Can you go through it again? These are the times, these review sessions are the right times to do these. So Unit 4 review, Unit 5. You don't have to wait for the end of the unit review to ask your questions. Anytime you have a question, fire an email. I'll either answer your question through email, or I can make arrangements to start talking to you a few minutes before class or a few minutes after class, sort out questions. If you have questions, you don't have to wait, but certainly this is a time to get caught up on any outstanding issues. So we will have Unit 4, we'll have our Unit 4 review, we'll start on Unit 5, we'll have our Unit 5 review, and then I have even squeezed in one final review session for the course on the Wednesday before whatever day is our final exam. And as soon as I'm aware of that, I think I'm going to try and put it on Friday of that week. Yeah, so there's these sessions coming up, but do your best and just work on those questions, work on those support questions, work on those key questions. And yeah, I'm available here to help. And I should be finished marking your midterms very soon. And as soon as I have them up, I will share them again with you on your dedicated Google Drives. If you can see here, up here, I've got dedicated Google Drives for each student. And this is where I've been returning your marked assignments for you. And this is where I will be putting your marked midterm to once I've finished marking it, and you'll be notified of that, okay? All right, I think, yeah, I've taken care of some So just last few things I wanted to make sure everybody knew. Okay. All right.
Okay, thanks, Miss.
Okay, no problem. You're welcome, and have a good night, everybody.
Good night.
Thank you. Have a great night.
You too.
Goodbye.
Bye-bye.